All right, so the next two sections, we're just going to highlight the most important parts because it's the end of this chapter that I really want us to focus on. So the definite integral is actually section 4.2, chapter 4, section 2, and the fundamental theorem of calculus is section 4.3. All right, and I'm just going to combine these into both. Now, back in section 1, we learned that if you had, let's say, some sort of curve, all right, and it starts at A to B, you could, in essence, find the area underneath this curve, all right, by drawing rectangles, all right? And one of the things we notice, at least I hope so, is that the more rectangles you draw, so the more rectangles, the better approximation that we're going to get. All right? But notice that in the previous section, I didn't say anything about calculus. It was a lot of algebra. It was just using what we know from what we learned like way back in the day and just applying it to a problem that we've never seen before. So in this video, we're actually going to kind of, I don't want to say kind of, we're just going to dive right in. So I'm going to give you the definition of what we call the definite integral. Oh boy, bigger than I thought. There we go. All right, so here's our definition of the definite integral. Now, I'm going to go ahead and read it real quick, and then I'm going to start to dissect everything here so you can see where everything's coming from. So we got if f is a function defined for a to b, and we divide the interval from a to b into n subintervals of equal width, we're going to call those widths delta x, which equals the quantity b minus a divided by n. So we've seen this before. We let x sub 0 equal a. In other words, the x sub 0 is going to be the very first part of the interval. Then you have x1, x2, x3, and x4, all the way up to xn, where xn is going to be equal to b. So if I scroll back up, this right here is x0, and that right there is xn, and then everything in between is going to be x1, x2, and so forth. All right? And sorry, I lost track. So we let x sub 0 equal a all the way up to xn, which equals b, be the endpoints of these subintervals, and we let x1, x2, xn be any sample points inside of the subintervals so that xi star lies in the ith interval of xi minus 1, comma xi. I know it's a lot. Then the definite integral of f from a to b is defined as, and this is the big thing here, okay? So this is read on the left-hand side. The integral from a to b of f of x times dx is going to equal the limit as n goes to infinity of the summation from I equals 1 to n of f of xi star times delta x. Now, I'm not even going to worry about the rest of this. This is so much to take in. But if you think about what we applied in the previous section, this right here actually is very simple to understand. So let me go ahead and let me demonstrate why I'm saying that. All right. The first thing is this. All right. If I just got rid of all this stuff over here, I don't care about any of this. Notice this is nothing more than the height and the width of one rectangle. And we know if we have the height and the width, that is going to equal the area. Okay? Now, I'm going to erase a little bit here. What the summation is saying is, instead of starting with one rectangle, how about we start adding more rectangles in? and adding up all the regions. So the summation symbol, sigma, this is sigma, and this means the add. All right, so all you're doing is, and I'm going to zoom in here so we can really see it now. All we're doing is we are going to be adding I equals, we're starting with one rectangle, and then we can go to any number of rectangles that we want. That's what the letter N stands for. So if we wanted 4 rectangles, I would have a 4 up top. So 1 to 4 rectangles, add them all up, tell me what the area is, all right? And this is the fun part. This is where the calculus kicks in. Because remember, in the previous section, we looked at examples where we had 4 rectangles or 5 rectangles or whatever. But what if I said, instead of 1, 2, 3, or 4 rectangles, what if I let the limit as n goes to infinity? In other words, an infinite amount of rectangles. And that, everyone, is a calculus concept. So if we allow the limit as n goes to infinity, what we're really saying here is, instead of having the letter n, what if we had infinity here? We are going to be adding up an infinite amount of rectangles. And that is what we call the integral from a to b of f of x multiplied by dx. That's what this is right here. And this, if you're thinking about this symbol, this integral symbol, as like the letter S, you are absolutely correct. It's just a letter S that we elongated. That's it. All right? Leibniz is responsible for using this notation. And it's actually really intuitive when you think about it. Okay? So this is what we call a definite integral. And why do we call it a definite integral? Because I don't think you're ever going to find this in a book. This is just like my way of thinking about it. But you definitely know where you were starting and where you were ending. And you're going to be drawing an infinite amount of rectangles. And you're going to be adding up all of those rectangles together. All right? Let me repeat that one more time because I went real quick there. So I want to just slow down just a little bit. And I'm going to erase a bunch of stuff here. So I'm going to erase a bunch of stuff because I just want this to be nice and clean so you can see exactly what I'm talking about, okay? Let me get out my highlighter here. All right, so here we go. So going from left to right, the integral from a to b of f of x times dx is the same exact thing as saying find the area of an infinite amount of rectangles and add up all of those individual areas. That's exactly what this definite integral is saying for us. Okay? Now, we have formulas that help us do this. But before we can do the formulas, all right, we need to understand really what's happening here, okay? So the first thing I want to do is just kind of dive into what this definite integral represents. All right, now I'm going to put this little multiplication symbol here once, but normally I would just write it like this, all right? And the reason why I'm putting this multiplication symbol here is because f of x represents the height of our curve, and d of x represents the width of each rectangle. Okay? The letter A is what we call our lower bound or lower limit. The letter B is our upper bound or our upper limit. And the elongated S is the integral symbol. All right. And off to the right, this is not you're not going to see this in a math book, but the way to think about what this integral symbol is, it's the limit as n goes to infinity of the summation from I equals 1 to n of f of xi star times delta x. In other words, it is all the rectangles that you're adding up and you're finding the areas of each rectangle. Okay? So that is what a definite integral tells us. Now, the definite integral will give net area. All right? So we're going to see what happens in a little bit when we're using this definite integral here, because we do got to be careful. All right? In fact, you know what? Why don't I just introduce it right now? Because your book actually has a pretty nice picture of what net area actually looks like. All right, so in your book, I'm just going to copy and paste this picture here. Here's an example of net area right here. All right, now if I wanted to write this in its most general form, this will be the integral from a to b of f of x dx, all right? And what you got to be worried about here is, here you have area under the curve. Here you have area under the curve. However, it's under the x-axis. That's why there's a negative sign here. And then here you have area above the x-axis, and under the curve as well. So what's going to end up happening here, all right, is that if you use from a to b, okay, you are going to get a net area. It's going to add this formula, adds these two areas together, and it's going to subtract this area away. Now, a way to get around that would be to sit here and say, okay, well, we're going to call this x, x1, and we're going to call this x2. All right? We can break this up into area 1, area 2, and area 3. So, if I wanted to find their true area, I'm going to have to add up each one of these little regions that I went ahead and labeled. And to write that out is actually not very difficult at all. In fact, it's going to be the area, or the integral from a to x1, whatever x1 happens to be of f of x dx, plus the area from x1 to x2 of f of x dx again, plus the integral of x2 to b of f of x dx. And that will give you the total area underneath this entire curve. All right? So you do got to be careful when you are setting up these problems. Now, for you, I am going to be showing you a bunch of graphs and everything, so we can start to navigate our way through this. But eventually, we should be able to get to the point where we look at this and go, okay, I got to be careful because I know I'm going to get net area. And 99% of the time, net area is what we want. But just realize that if the question says what is the total area, that's when you got to break things up. Okay? All right, so now that we kind of have an idea how this works, let's go ahead and let's look at converting between the two notations themselves. So here's an example right here where all I want you to do is express the limit as a definite integral. And it is not difficult at all. All right? It's going to look a little confusing at first, but once I show you how to do it, you'll be like, oh, that's so easy. I can't believe I didn't even see that. So we're going to go from the limit as n goes to infinity of I equals 1 to n of 3/4 times xi star to the 6th power minus 7 xi star times delta x, and the interval that we want is from 2 to 4. Now, the thing you got to remember here is this. Our definite integral is defined as the integral from a to b of f of x dx, which is equal to the limit as n goes to infinity of the summation from I equals 1 to n of f of xi star times delta x. All right? So I'm going to go ahead and use a highlighter here to kind of show you where everything's coming from. All right? First, we need our limits of integration. All right? So our limits of integration are the upper and lower bounds a and b. They're right here. That's the interval. I'm starting at 2 and I'm going to 4. So directly underneath, I'm going to write 2 to 4. Now, f of x is the actual function itself, which is right here in green. So f of x, all right, is going to be 3 over 4 x to the 6th minus 7x, okay? Because when you think about this, the xi star is just a representative sample within all these sub-intervals that you've created. So we just want what the function is. 3/4 x to the 6th minus 7x. All right? And then finally, our change in x is dx. So I can just write dx right there. And that is how we take a limit and express it as a definite integral. I hope that makes sense. It's much easier than what people kind of make it out to be sometimes. It's just there's a lot of things going on in this up top here. But like I said, if you understand section 1, which is you're creating rectangles underneath a curve and you're adding them all up and you're adding an infinite amount of them up, all this should look fairly similar, okay? All right, so the next question becomes, now that we understand what a definite integral is and how it relates back to the limits, how do we evaluate integrals? Now, I'm just throwing this out there. Evaluating integrals strictly using algebra is very difficult. Let me write that down. Evaluating integrals using algebra requires us... Why's my handwriting so bad? Requires us to use something called, and if you've never heard of these before, there you go. And if you go into Appendix E into your book, all right, you're going to find all these, okay? But they're called Riemann Sums, all right? Now, in general, we have some, it's funny the way I say that. We have some formulas that we already know. All right. So like, for example, the summation from I equals 1 to n of I is equal to n times n plus 1 over 2. Now, what I'm talking about here is this. If you wanted to take, let's say, the summation from I equals 1 to 3, all right, of I, then what we're really asking you to do here is just add up the numbers from 1 to 3, 1 plus 2 plus 3 equals 6, and tell me what that equals. This formula, n times n plus 1 divided by 2, actually gives us the summation from 1 to n of any amount of numbers. All right? So, real quick, because I don't want to deviate too far away from calculus, but I'm going to prove this formula here for us, all right? And I'm going to use a story, and it's a very well-known story in the world of mathematics. And it deals with Gauss, famous mathematician Gauss, okay? So basically what happened was, and the story goes that when Gauss was in primary school, teacher came into the room and said, hey, do me a favor. I want you to add up all of the numbers from 1 to 100. So what the teacher was really saying is, find a summation starting at 1 and going to 100, all right, of n. Now the answer to this would be 1 plus 2 plus 3 plus 4 plus ... all the way up to 100. And the answer is actually 50-50. Now, if you are in calculus class, and if you sat down and did this, it would take you some amount of time. Maybe 10 minutes, maybe 20 minutes, maybe 3 minutes with a calculator. I don't know, all right? But you got to understand, Gauss, they didn't have calculators back then. They had to do everything by hand. So here's what Gauss did, all right? So Gauss thought about the question, all right? And Gauss said, well, Gauss sat down, remind you, primary school, all right? That's like, I don't know, 1st through 8th grade or something like that. Gauss thought about it like this. Gauss said, well, the teacher wants me to add 1 plus 2 plus 3 plus 4 all the way up to m, and I know that is going to equal a sum. Okay? That's going to equal a sum. So then Gauss took a step back and said, well, the teacher wants me to go to 100. So here's what Gauss actually did. He started listing some terms. And like I said, he knew it equaled a sum. But then he made a really interesting connection. And I'm going to show you it right here. 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. And since there are 50 pairs of numbers in between 1 to 100, and he knew that when you add up 1 plus 100 and then you move inward, so 1 plus 100, 2 plus 99, 3 plus 98, and so forth, all Gauss did was took 101 times 50 and found the answer to be 5,050. Now, Gauss did this within 5 minutes. And it was absolutely staggering how he thought about this, because completely thought about it the exact opposite way. In fact, I would argue some of us watching this video right now would have done 1 plus 2 plus 3 plus 4, found a total, plus 5 plus 6 plus 7 plus 8, found a total, and you would have kept doing it in a linear fashion. Gauss did not think in a linear fashion. Gauss, all over the place. So he presented this answer to the teacher, and the teacher said, well, that's fantastic. But how do you know it always works? And Gauss sat back down and thought, all right, well, if the name of the game is just to keep adding up numbers to any number that you want me to, call it the letter n, and I know this is going to equal a sum, and he also knew that if you started, if you started to take this number on the outside and this number on the outside and combine them, all right, and here's how he did this, all right, because it's not that intuitive if I'm just talking to you about it, so I'm going to have to write this out. So give me 1 second. Oops. All right, so this is the way Gauss thought about this, was if you wanted to go to 100, then obviously this would be 99, and this would be 98, because 100 minus 2 is 98, and 100 minus 1 is 99, and so forth. Here's what Gauss did. He flipped it. He said, all right, well, I'm going to take this right here. I'm going to flip it and write it underneath. So This is going to be n. This is going to be n minus 1. This is going to be n minus 2. And I'm going to continuously do that until I get all the way down to 3, 2, and 1. And that has to equal a sum. So all we did was literally just reversed it. And he added these two equations together. And notice when you add these two equations together, you're going to get n plus 1 plus, and I'll do it for the first one here. Underneath, you got 2 plus n minus 1. Well, that's going to be n plus 1. And if you keep doing that, you will always get n plus 1, no matter what you do. And on the right-hand side, you're going to get 2 times the sum. Now, since you have no idea where you're stopping with these n plus 1 terms, you are going to have n of them. Therefore, we get n times the quantity n plus 1 equals 2 times our sum. And then finally, if we just divide both sides by 2, we get n times n plus 1 divided by 2, which is the sum. And if you remember, we defined the sum. We defined our sum as 1 plus 2 plus 3 all the way up to the letter n. And this is just a very long, drawn-out way of writing the summation of I equals 1 to n of I. And that is one of the formulas that we would actually use when we evaluate integrals using algebra. And there are other ones. So let me go ahead and write the other ones out. And I'm only going to do one example, and I'm only going to give you one problem to do on your homework like this. Because like I said, it's very difficult, it's very time consuming. And if you are not familiar with summation notation and how summations work, which are actually quite simple, they follow the linearity rules. So you can distribute them, you can add and subtract them, you can do a bunch of things with them. But if you've never seen it before, it gets very difficult to work with. So here are some known formulas. The first one is what we have up above. The second one is going to be the summation. I'm having a really hard time writing my summations today. Normally, I'm not too bad. So this is going to be the summation from I equals 1 to n of I squared. And you can actually prove this the same exact way that I did above. But this is just going to equal n times the quantity n plus 1 times the quantity 2n plus 1 divided by 6. The other one would be the summation from I equals 1 to n of I to the third. And this is going to be n times n plus 1 squared. I'm sorry, n times n plus 1 over 2 quantity squared. And then there are some other properties. All right, so these are properties. And notice up above the formulas, I stopped at I to the third because I to the fourth is crazy. I to the fifth. And there are other summations for all different types of functions. Like, for example, the summation notation of e to the x is equal to, you can write the summation notation as this. The summation of n equals 0 to infinity of x to the n over n factorial. That is how you approximate e to the x using summation notation. And there are a bunch of these that exist. Luckily for us, I am not going to be going over this. However, if you happen to see me in Calculus 2, we do this. All right? So maybe over the summer, learn summation notation. Grab a pre-calc book, start reading it. Now, some properties that we do got to be concerned with, and they're not difficult at all. The first one is the summation of a constant is nothing more than n times the constant. So in other words, if you wanted to do from 1 to n of, let's say, 4, it would be n times 4. And however many times you need to add 4, you would just do that. Another property says that if you have a constant, you are allowed to pull the constant out front of the summation symbol. So let me go ahead and write this. So you have a constant multiplied by some sequence of numbers, AI. This is going to equal C times the summation from I equals 1 to n of the sequence AI itself. All right. So like I said, I don't want to get us too bogged down with all this summation stuff. Okay. There are 2 more properties. I'm going to combine them into one because they're both the same. And that is just if you have 2 different sequences being added or subtracted, you are allowed to distribute your summation symbol. All right. In your book, they have all of these listed, but they don't prove any of them. All right. Actually, no, I'm lying to you. I think they prove like 1 or 2, but not enough for you to really get a full grasp. All right. What I'm really concerned with is how do we evaluate a definite integral using Riemann sums? All right. So the example that I'm going to do, I'm going to evaluate the Riemann sum for f of x equals x to the third minus 6x. My sample points are right endpoints. All right. And I'm starting off at a equals 0. I'm going to b equals 3 with n equals 6, or 6 rectangles is what I want. All right. So what I'm going to do here is I'm just going to go ahead and graph this real quick. All right. So here's our graph. All right. Oops, sorry. And I'm just going to walk us through this. It's not difficult at all. All right. So when we're using Riemann sums, all right, we're going to be using the definition of the definite integral. Okay. Now, using Riemann sums, so Rn, which is a Riemann sum, is going to equal the summation from I equals 1 to n of f of xi times delta x. All right. Now, we want 6 rectangles. So this is going to be R6, which means we're going to be adding up from I equals 1 to 6 regions, or 6 areas. Let me try to move this down a little bit here so it looks better. All right. There we go. Of f of xi delta x. Now, we know f of xi. That is nothing more than just x cubed minus 6x. The question becomes, what is delta x? Because remember, we need to add up rectangles here. Riemann is just telling us add up 6 of them. So delta x, we learned, is b minus a divided by n. So delta x is going to be 3 minus 0 divided by 6. Therefore, delta x equals 1/2. So the width, oops, I forgot to write delta x. So the width of each one of my rectangles is 1/2. So I'm going to come over to my picture. I'm going to be using, as the directions say, right endpoints. So right here is going to be my first rectangle, and here is the right endpoint, and I draw this over here. And there is my first Riemann sum right there, R1. Now I'm going to keep doing this. Here's R2. Here's R3. Here's R4. There's R5. And there's R6. And the reason why I wanted to shade R5 and R6 is because I wanted to demonstrate that these two rectangles are above the x-axis. Now, we are going to get a net area here. All right, so just be aware of that, okay? So all we have to do now is just go ahead and figure out what this is using Riemann sums. So for us, this is going to be very simple. R6, which is our Riemann sum, is going to be nothing more than the summation. I'm just writing out the definition one more time. Of I equals 1 to 6 of f of xi times delta x. Now, we know from earlier, we could factor out the delta x. So all we have to be concerned with is f of 0.5 plus f of 1.0. And we just keep doing this all the way up to 3. All right. So R of 6 is going to be 1/2 multiplied by, and I'll do the first one here for us, but then I'm going to leave you to do the rest. So f of 0.5 is going to equal 0.5 to the third power minus 6 times 0.5, and that is going to be equal to negative 2.875. And all you got to do is repeat this process for f of 1, f of 1.5, f of 2, f of 2.5, and f of 3.0. And if you do that, you're going to get the following numbers. F of 1 is 5. F of 1.5 is negative 5.625. F of 2 is 4. F of 2.5 is 0.625. And f of 3 is 9. And when you add all these up and multiply by 1/2, you should get negative 3.9375. All right. So notice that f is not a positive function, and the Riemann sum does not represent a sum of the area of the rectangles, but it does represent the sum of the areas of the blue rectangles minus the sum of the area of the other rectangles. So this blue rectangle is here, and the Riemann sum represents the area of all of these, which we know to be underneath the x-axis, so it's a negative. These are above the x-axis, so it's just going to be a negative or plus and a minus, which makes it a negative here in terms of the area. All right. Now, to do this using the interval notation that or not the interval notation, the summation notation above. All right. Like I said, it's much more difficult. So we're going to evaluate the integral from 0 to 3 of x to the third minus 6x dx. All right. Now, in order for us to do this, we need to use those formulas from above. So let me go ahead and just let me write some of this stuff out first, and then I'll explain what it is. All right, so here's what we got. All right, and like I said, this is very difficult, so just follow along. I wrote a lot, but I'm not even like done yet, but I just want to walk through this. So at the very start of this, we know that our definite integral is defined by the limit as n goes to infinity of the summation of I equals 1 to n of f of xi delta x. Now, we also know delta x is going to equal b minus a all over n. Therefore, if I want to evaluate the integral from 0 to 3 of x to the third minus 6x dx, here's what I'm saying. I do not want, and I'm scrolling up real quick, I don't want these little blocks here. I want an infinite amount of them. Okay? So in order for us to do that, all right, we need to go ahead and we need to rewrite our problem a little bit. So first, if we want to evaluate from 0, or I'm sorry, if we want to evaluate the integral of 0 to 3 of x to the third minus 6x dx, the first thing we need to figure out, what is our change in x? So our change in x is going to be dx, which is the endpoint minus the initial point over n, because we don't know how many, well, actually, we do know how many intervals we want. We want n of them, which is an infinite amount. So delta x is going to equal 3 over n. So when you think about this, your first interval, or your first rectangle, is going to be at 0. Then your next rectangle is going to be at 3 over n. Then your next one is going to be over 6 over n, because 3 times 2 is 6 over n. And if you keep doing this, we come up with this right here, where xi, in other words, any right-ended rectangle that we want to draw is going to be located at 3i over n. So I'm going to take that information. Actually, I went too far. There we go. I'm going to take that information and I'm going to rewrite my definite integral. So here's my definite integral again. I'm underlining it. So the integral from 0 to 3 of x to the third minus 6x dx is going to be equal to, this is the limit definition now, the limit as n goes to infinity of the summation of I equals 1 to n of f of 3i over n, because that's what x is. Remember, this is a function. It's f of x. In this case, x is 3i over n, times 3n, which this right here, all right, is our delta x, all right? So now we can finally start to evaluate this. So down below, this 3 over n is delta x, which is a constant. So I'm allowed to take this and move it all the way up front. And that is why I have the limit. Actually, I don't want to put it all the way in front of the limit. I want to put it in front of the summation. My bad. So that's why I have the limit as n goes to infinity of 3 over n times the summation from I equals 1 to n of x to the third minus 6x. Is just, since x is now equal to 3i over n, I put 3i over n to the third minus 6 times 3i over n. All right? Now, I know this looks crazy at first, but this is nothing more than the limit as n goes to infinity of f of x times delta x. In reality, we know the commutative property states order doesn't matter when you multiply things. So remember, off to the right-hand side, 3 times 2 is the same as 2 times 3. So all I did here is I just put the delta x out front, and I want to multiply times f of x. So it's still the same thing. It's just I made a lot of substitutions, okay? Now we're going to go ahead and we're going to solve this, okay? And like I said, this is a little bit easier said than done, but if you just take your time and you follow along with me, it's not as bad as what you think, okay? So we get the limit as n goes to infinity of 3 over n times the summation from 1 to n of 27 over n to the third, I to the third, minus 18 over n I. All right. Now, we're going to apply some of our properties. I have the summation symbol, so I'm going to distribute that. That's going to give me the limit as n goes to infinity of 3 over n times the summation of each one of these so just let me go ahead and write this out real quick. All right. And then from here, notice 27 over n and 18 over n, they're going to be numbers. If I knew what n was, and we have an idea, n's going to infinity, right? We have an idea, n is going to infinity there. So if I knew what n was or what number we're talking about, they would be constants. Like if n was 15, it would be 27 over 15 and 18 over 15. And what that means is I can pull them in front of my summation symbol also. And hopefully you can see where I'm going with this right now. Because by now, some things are starting to jump out. Oh, sorry. Let me write this cleaner. 18 over n, and then the summation symbol of I. So then I get the limit as n goes to infinity. I'm going to take this 3 over n, okay, and I'm just going to go ahead and, excuse me. Okay, so here's our goal. We want summation symbols with a formula like I or I to the second or I to the third. Like we want to get things like this, okay? Now notice within what we have above, we definitely have the I thing, but it's a little bit more complicated. Like, for example, right here we have 3i over n, and here we have 3i over n. So what we're going to do is we're going to use algebra to actually simplify down in this stuff that we know, using those formulas from above, all right? So please follow along, all right? If you need to, pause the video, go back, think about what's happening, all right? But I'm going to go ahead and just use just a bunch of algebra here. So we have the limit as n goes to infinity of 3 over n times the summation of I equals 1 to n of, now I'm going to cube it first, so I get 27 I to the third over n to the third minus 18i over n. All right. Now the next move is just understanding what's happening here. I know that the 27, and let me get my highlighter out here. I know this and this 27 over n to the third is going to be a constant number, because if I knew what n equals, and we know it's going to infinity, but if I knew like if n equaled 100 or 1,000 or so forth, I would just substitute that in, but regardless, it would be a constant. So my goal then here, all right, is I'm just going to go ahead. I'm going to distribute my summation symbol so I can apply that one constant rule. So let me just erase this and move it down a little bit. So here's what I'm saying right here. We're going to do the limit as n goes to infinity of 3 over n, bracket, and I'm going to go ahead and just, like I said, distribute the summation symbol. That's one of the properties that I listed above. And then I'm going to take any constant and letter n together, and I'm going to pull it out front of each one of these summation symbols. So I get 27 over n to the third times the summation of I to the third minus 18 over n times the summation from I equals 1 to n of I. And now hopefully you can see that what I've done algebraically is I simplify this down so I can start to see some of those Riemann sum formulas from above. Okay? Now remember, this is not giving me little rectangles. This is giving me an infinite amount of rectangles. Okay? So my next move here, I'm going to distribute the 3n. So it gives me the limit as n goes to infinity of 3 times 27, that's going to be 81 over n to the fourth times the summation of I to the third. And sorry, I forgot to write my I equals 1 to infinity for that first one. Minus 3 times 18, I think that's 54. So we're going to get 54 over n to the second times the summation oh my gosh. Summation symbols are so hard to draw sometimes. I equals 1 to infinity. I'm sorry. Why did I write infinities? Hopefully you're yelling at the screen right now. You're like, no, there's supposed to be n's. All right, so from I equals 1 to n of I. Whew. Okay. So far, so good. We're almost home free. Okay? Here's what we know. We know these formulas for the summation of I equals 1 to n of I cubed and the summation I equals 1 n of I. So we're going to go ahead and substitute those formulas in. So we get the limit as n goes to infinity of 81 over n to the fourth multiplied by, now for I cubed, if you look above, okay, that's going to be n times n plus 1 quantity squared minus 54 over n to the second multiplied by n times n plus 1 over 2. All right. Now from here, we get the limit as n goes to infinity of, now you got to be careful. This turns out to be n to the second times n plus 1 to the second over 4 minus, I'm going to go ahead and simplify this real quick. It's going to be 27 times 1 plus 1 over n. And then I can simplify the first term a little bit more. it's going to be 81 over 4 times 1 plus 1 over n squared. All right, and finally, what we can do here, now that we have everything simplified, we're going to make our limit substitution. We know sorry, I'm just going to write it out real quick just so I can write some stuff. All right, here we go. So we know this 1 over infinity basically goes to 0. 1 over infinity goes to 0. So that's going to give me 81 over 4 times 1 minus 27, which equals negative 27 over 4 when you find your common denominator and everything. And if you were to divide these two numbers, you get negative 6.75. So you could clearly see there's a difference here in answers. All right? There's a difference here in answers, and that's okay. All right? Because the Riemann sum does not represent the sum of the areas of the rectangles. It represents the sum of the areas of only the above rectangles minus the sum of the rectangles underneath. Let me scroll all the way back up. This number, if you use rectangles, gives us net area. However, this is the total area. All right? Now, hopefully you could sit here, and I'm going to zoom out as much as I can. Sorry, I know it probably looks really small on your screen, but there's a lot of algebra involved, and it involves a lot of summation notation. And if you're not familiar with that, not a big deal. I'm not going to be testing you on that. But you got to be sitting there asking yourself, is there a better way? And the answer is absolutely. All right? So what I want us to do real quick is just kind of define the fundamental theorem of calculus part 1. All right, so I promise I'm going to make this nice, short, and sweet. This is section 3. And we're going to be talking about the fundamental theorem of calculus part 1. There is a part 2, but we're going to look at part 1 first. Now, if you think about what we've been doing this whole time, we've been finding the area underneath the curve. All right? Now, there was one very special problem that we looked at. All right? And we looked at the distance problem. All right? And what we gave you when we were talking about the distance problem, and I'm just going to draw just an arbitrary graph real quick, is we gave you the velocity. But if you think about the relationship of what we've been doing in this class, which is calculus, I'm giving you the velocity, but we're finding the distance. And if you remember from differential calculus, if you knew displacement, which is distance, it's just where the object is moving, and you took the derivative of displacement, you end up getting the velocity. Well, it just so happens that if you have velocity of an object and you integrate the velocity of the object, you end up getting the displacement back. And that is what we're going to be doing here. So the first part of the fundamental theorem of calculus basically tells us that if you have some function, let's call it g of x, this is going to equal the integral from a to the x of f of t dt, meaning that if f is continuous on some interval a to b, then the function g defined by And I'm going to write it again. G of x equals the integral from a to x of f of t dt between a and b is continuous on the closed interval from a to b, and this is the biggie, differentiable on the open interval. And what this implies is that the derivative of g of x is going to equal f of x. So here's what this is saying in a nutshell, all right? Is that if you integrate some function, you're going to get another function such that if you were to take the derivative of that function, you end up getting back the original answer or the original function. And if you think about it in terms of velocity and displacement, if you integrate velocity, you can find displacement. And if you take displacement and take the derivative, then you can find the velocity, all right? Which means differentiation and integration are inverse processes. Much like adding, subtract, or inverses, multiply and divide, square root and square, derivative and integration are inverse processes, which means there is a relationship between these two. And we can use all that information that we have from derivatives, and we can apply it to integrals, and we take all the information from integrals, and we can apply it to derivatives as well. All right? Whew! That's a lot. All right? So what I want to do now is just go ahead and give you the overall idea of the fundamental theorem of calculus, parts 1 and part 2. So, the fundamental theorem of calculus. This is the biggie now. Here's part 1. Actually, let's do this first. Let's suppose f is continuous on a closed interval from a to b. Part 1 says, if g of x equals the integral from a to x of f of t dt, then the derivative of g of x equals some function of x, all right? And that function of x is when you substitute in x for t, okay? Part 2 says the integral from a to b of f of x dx is going to equal f of b, capital F of b, minus capital F of a, where f is any antiderivative of f. All right? In other words, the derivative of capital F equals little f. All right? So, part 1, and I realize this is probably extremely confusing right now. So let me rewrite part 1 in an easier way to kind of understand it. Part 1 says basically this. Oops, give me 1 second. Part 1 says that if you take the derivative of the integral, they're inverse processes, all right? Which, it's going to be very bad of me to say this, but if you want to think of them as like ugh, and I hate saying this, but if you want to think of it as like canceling themselves out, it kind of does, but it doesn't, okay? What it's telling you is that if you were integrating and you take the derivative, you are basically like taking a zipper and zippering it up and then zippering it down like on a jacket, okay? Now, if you do that, you're going to be left over with whatever function you've started with, all right? So an example of something like that, all right, would look something like this, okay? So, if I'm using the fundamental theorem of calculus, part 1, FTC 1, all right, find the derivative of, now watch how I write this here, okay? This is going to be g of x, which equals the integral from 5 to x of t minus t squared, all raised to the 8th power, dt. Now, if you look above, all right, if you look above where I have part 1 written here, all right, what we're really doing here is we're taking the derivative of this, all right, and by doing that, all we're doing is just substituting the x, because the derivative and the integral, like I said, in a sense, they kind of cancel themselves out. So taking the derivative of both sides then is going to give me g prime of x, which equals x minus x to the second, all raised to the 8th power. Okay? So that's what the part 1 says. Part 1 says that if you have the derivative of the integral, you get the original function back. So the original function, x minus x squared, all raised to the 8th power. All right? Now, if we go back to the second part, what part 2 is saying is that if you have the integral from a to b of some function of x times dx, what you're going to do is find the antiderivative. Now that's a new word. We haven't gone over that yet, but I will. So you're going to find the antiderivative of f of x. And what you're going to do is you're going to evaluate when x equals b, and you're going to subtract it away from when you evaluate when x equals a. We haven't done this yet, all right? We haven't done that yet, and that's fine. The only thing I want you to be responsible for is understanding for this week, part 1, all right? So part 1 just says that if f is integrated, the result is differentiated, we arrive at the original function x. That's all part 1 is saying. Let me write that down. I think that's a really nice, concise way of saying it. So part 1 says if we take f and integrate, and then the result is differentiated, we get the original function. All right. So what I want to do is just a couple more examples using part 1. Okay. Just so you can see how it works. And like, once you see it, you're like, oh, that's really simple. I, didn't even think of it that way. And then next week, we're going to be focusing on part 2. And part 2 is huge. So for example, let's go ahead. Let's do this one. Using the fundamental theorem of calculus, part 1. find the derivative of the function. All right. So we got h of x equals the integral from 2 to 1 over x of sine to the fourth t dt. Well, according to Fundamental Theorem of Calculus Part 1, the derivative is just going to give us the original function back. Negative sine to the fourth 1 over x, all divided by x squared. All right. So I'm going to leave you with this. The examples that I have in the homework are very simple. All right. Because what I want you to do is internalize this right here. All right. If we take f and we integrate, and then the result is differentiated, we get the original function back. Next week, we're going to be talking about part 2, and I'm going to show you all these different antiderivatives. And you are going to thank me because they're formulas and they help us to do any type of problem. So on that note, I will see you in the next video.